Welcome to the chapter related to the computation of loads for a wind turbine. Let's start with a reminder on why loads should be computed. The goal of using SAMSEF for wind turbines loads or similar tools is to evaluate the dynamic loads acting on transmission components of large flexible wind turbines. But where do these loads come from? Well, these machines are called wind turbines for a reason. So obviously, wind is the major source of loads to take into account. Wind closely interacts with the machine, and aeroelastic loads produced by wind depend not only on the wind's strength and direction, but also on the behavior of the machine, especially on the deformation and vibrations of the blades. So, computing loads separately and using them as fixed input is not a very accurate approach. Control commands are also a source of loads acting on the machine. These will have two impacts. They may apply direct loads to make the machine move via yawing or blade pitching, for example, but they will also influence the aeroelastic loads by changing the position of the machine with respect to the wind. Vibrations are produced by the interactions between the machine and both wind and control commands. These vibrations are, of course, closely linked to the dynamic loads acting on the structure. Vibrations will be more significant as the size of the turbine, as well as its flexibility, increases. It's necessary to compute these dynamic loads very accurately because they will be responsible for fatigue phenomena and local stresses in structural components. Proper design of these components requires accurate loads as input for the computations. Loads computed at this stage will be used in two different ways. First, they will be transformed into equivalent static loads to be used as boundary conditions on finite element models of components. Stress distribution and potential weak points will then be computed from there. Loads can also be used as input for gearbox design. In that case, we would evaluate the behavior of the gearbox subjected to these dynamic loads, including potential backlash and bearing behavior, transmission errors that eventually might increase vibrations, as well as fatigue phenomena, both on bearings and on gear teeth. So, we can conclude from this first part that it's important to compute these loads accurately, as they will be used as input for component designs. Tension, bending, and torsion are equally important, and potential coupling among them should be taken into account. If loads are underestimated, durability will likely be wrongly assessed, and components will fail earlier than expected, leading to maintenance headaches or, even worse, prolonged time during which the turbine is down. On the other hand, overestimating loads usually leads to overdimensioning, so that turbines end up being more expensive than they really should be.